All right, so 15.1, part 2. There was a lot in this beginning section. All right, divergence. What's that? How do you say divergent? Divergent? Is there a movie called Divergent?
It's
About an infinite series. So I get. See, now if it would have been clever, I would have said there's a movie called Divergent, and then you would have said yes, and I would have said seriously. All right. So we know about vector fields now. We know a little bit about vector fields. What a vector field is. We know how to tell if a vector field is conservative. We gave some tests for conservative vector fields, and we talked about how we produce if we have a conservative vector field, how we figure out the potential function, and we talked about the curl. Another important operation that we're going to use with vector fields is the divergence. So we'll start by defining divergence. Our divergence. So we'll do. So our vector field F, and we'll just do the three-dimensional, the space vector version. If we're in a plane, we just have one less component. So we're going to say our field is Mi plus Nj plus Pk. The divergence and we'll write the divergence a couple of ways. You'll see div f. What we're going to do to produce this is we're going to do the dot product del dot f. And this is going to be the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. So we're taking the dot product of our vector operator, our del operator, with our vector field. It's important to remember here, since this is a dot product, the divergence is a scalar. So just like when we were talking about when we're doing dot products and cross products just with vectors and not with any vector operators, common mistake is for people to forget that a dot product is a scalar. The divergence, so we said the curl tells us something about the tendency of the vector field to cause a rotation. The divergence tells us about the tendency of the vector field to go outward or go inward. So divergence gives us this idea of going outward. If it's negative, it's going inward. So it tells us something about the vector field. The vector field's tendency to flow outward is the way we usually say it. We'll make that a little more precise towards the end of the chapter. The divergence of the curl of f is always 0. So we're saying that del dot del cross f is 0. So the divergence of the curl is 0. And we'll verify that with one of our examples. And remember Just as a reminder, we're using the del, our del as a vector operator. So we're saying that we're thinking of del as the partial with respect to x of I hat, partial with respect to y, and this is just another reminder, j hat, plus a partial with respect to z, k hat. So del is this vector operator. And that's how we end up with this as our dot product. All right, so I just want to we'll do one example of calculating the divergence of a vector field. We'll verify that the divergence of the curl for a particular vector field is 0, just to do the calculations. And then I have a couple of true-false questions, and that's all we need to do today. So everybody good with our definition of the divergence? Okay. So are you conducting another class there on the side? Carly's teaching what we really need to learn over there? Or maybe translating what I'm saying? All right. Let's find, so we're going to find the divergence.
It looks like it's like demon like eyes. Nothing is there. It's like the horse at the What tipped you off the fact that
All right, so there's our vector field. We want to find the divergence of this vector field. So we're going to find del dot f. So we'll take the partial with respect to. We're going to form our dot product. So let me just write this out. So we're saying that this is d dx, just to make everything explicit, plus d dy j hat plus d dz k hat. And we're forming the dot product with sine x I hat plus cosine y j hat plus z squared k hat. So we're going to take the partial with respect to x of the x component, and we get cosine x. Take partial with respect to y of the y component, we get minus sine y, and partial with respect to z of the z component here, plus 2z. And that would be our divergence. And then if we need to calculate the divergence at a particular point, we just plug our point in there and calculate. Notice that we got a scalar. Our divergence is a dot product, so it's a scalar. So questions on calculating? Do we need to do another example of calculating the divergence? Everybody good with doing this dot product? All right, so let's verify, for our next example, let's verify that the divergence of the curl of a particular field is 0.
You can't take the curl of divergence, can you?
We'll talk about that in just a second. We want to verify that this is 0 for f, our vector field, is x, y, z I hat plus y, j hat plus z, k hat. So we want to verify this. So we'll do the cross product first. So del cross f. Set up our determinant. Oops, I forgot my partial derivatives here. So there's our curl. When we calculate this out, we take the partial with respect to y of z. We get a 0 minus the partial with respect to z of y, a 0. For the j component, we get the partial with respect to x of z, so we get another 0. Partial with respect to z of x, y, z, so we get minus xy plus k hat. And our last one, partial with respect to x of y, we get 0 minus partial with respect to y of xyz, so we get xz. So we get xy j hat minus xz k hat. And we want to take the divergence of this, so del dot xy j hat minus xz k hat. Take the partial with respect to x of the x component. Well, there's no x component, so I get 0. Partial with respect to y of the j component, I get an x. And partial with respect to z of the z component, I get a minus x. And we verify that it equals 0. So there's just a couple of kind of mechanical calculations there. And we'll end up, so what we're going to do with the divergence is we're going to integrate, one important thing that we're going to do is integrate the normal component of a vector field over a surface and relate that to the divergence of the vector field. All right, are we good with this? All right, I have a couple of true or false questions for you. True or false, and why? So the first one, if we have this vector field f, and we have a 4xi minus y squared j, then the magnitude of our vector approaches 0 as xy approaches 0, 0. So we want to know, is this true or false? So what is the magnitude of this vector? Square root of 16 x squared plus y to the 4th. Does that approach 0 as x and y approach 0, 0? That's a nice polynomial, easy. So that approaches 0 as xy approaches 0, 0. So that one's true. That one was an easy one. Next one. Call this number 1. Number 2. If for the same vector field, if our point xy is on the positive y-axis, the vector points in the negative y direction. So same vector field. So if our point is on the positive y-axis, then our vector points in the negative y direction. Is that true or false? True. Also true for the negative y-axis. So if it's on the y-axis, period, right? Because on the y-axis, x equals 0, and y squared is always, well, this part, y squared is always positive. So we have this negative sign, so we don't get anything that's going to cancel with the negative sign. So this y component is always negative on the y-axis. So that would be true. So this would, we didn't write this here, so this is true. This one is a true. Next one would get a little trickier. F is a scalar field. We can find del cross F. True or false? We can't perform this operation with a scalar. F is a scalar field, so we're saying we're taking the cross product of a vector operator with a scalar. So this would be a false. The curl only has meaning for a vector field. So we have to take the cross product of vectors. All right, last one. F is a vector field. And we're saying that del cross F equals 0. F is irrotational. But not conservative. So let's break it apart one piece at a time. We said that if del cross F, if our curl is 0, that was our definite, that we defined that field to be irrotational. But we're saying it can be irrotational and not conservative.
That is false, because for the irrotational and mixed partials, you have to be equal for them to cancel out, but that would make it conservative.
Right. So what Chalfin is saying is if the curl is 0, it has to be conservative. So irrotational and conservative mean the same thing. We said that a field is irrotational if the curl is 0, and we also said that that was our test for a conservative field. So irrotational and conservative mean the same thing. So to be conservative, our mixed partials are equal. Same thing for irrotational. So the curl equals 0, the field being irrotational, and the field being conservative all are the same thing. What were you going to say, Matt?
0 out of 9.
Could the curl be 0, and this should be a 0 vector? Could it be conservative at a point, or 0? Could the curl be 0 at a point, and have the field still be conservative? Not conservative. I think so. If our curl is 0, our curl has to be 0 for it to be conservative. So if it's 0 at a point, are you saying the curl is 0 at a point? Yeah. At a single point. I'll have to think about that one. Could we have the curl 0 at a single point and have it conservative everywhere else? I'm not sure that's possible, but I'll have to think about it. It's a good question. All right, this one is false, and then let me ask one more that was inspired by Will over there. We can find the curl of the divergence. So Will said, can we find the curl of the divergence? No, we can't find the curl of the divergence because the divergence isn't a vector. So what we'd end up with is something like this. We'd be trying to find the curl of a scalar. So this one is false. Divergence is a scalar, and so we can't find the curl of a scalar. All right. So we good so far with the idea of the divergence. Divergence is a little easier to work with than the curl, but not any less important.
A bumblebee.